Hello, everybody. My name is Vitaly Aksionov, and welcome to our second podcast of Heads of Hydra. So the first podcast was with Albert Cohen. If you haven't seen it, please look there on YouTube. With me today will be Vladimir Sitnikov this time, instead of Alexei Fedorov, but I'm happy to have him here because he's put enormous effort into combining their Hydra conference. Like, this is amazing what he has done there. And he wanted me to present him as performance engineer at Netcracker. So kind of, we are moving from theoretical background to more practical background this time. And I'm happy to welcome Danny Hendler, who will be our guest for the next 1 hour or so. He's the professor of Ben-Gurion University and head of the computer science school there, right?
Yeah, computer science department.
Computer science department, yeah. So, yeah. Okay, so let us start probably with a simple question then. So we will talk with you about biography, and then we will move to the topics that you were recently, you were interested in the past, and now you're recently interested in. And the first question is that I'm not sure, it was pretty hard to find any information about you before 2001, when you came back to the computer science, like as somebody, like as anyone knows that Danny finished his PhD, then he moved to the industry. I don't know like exactly where, so he will tell us. And then he moved back to computer science. So it's kind of the history of the great achievement that computer science wins against industry here.
Yeah, so actually I started in the high tech. Wow, this is really long ago, but I would say at 1983, and I worked in the high tech for 18 years, obtaining my first and second degrees during this period. And then I returned to do my PhD at 2001, completed it at 2004, 2 years of postdoctoral research, and then I joined Ben-Gurion University at 2006. So up until 2001, I was in the Israeli high-tech.
Okay, high-tech is the company, or
no,
what is the name?
Is the sector.
Yeah, okay, so this is the... No,
Yeah,
sure. I thought that this is the name of the company, so kind of high tech. It can be the name without H at the end, you know, high tech without H. So where have you been working, and why you decided to go back to the computer science?
So I've been working at quite a few companies, starting with LSynth, which no longer exists. It did medical imaging software. And then Telrad, National Semiconductor, Sun Microsystem. Also, it does not exist anymore. It was bought by Oracle, although it left us with many very nice technological developments and softwares, as we all know, Java, NFS, etc.
And what have you been doing? What have you been doing there? Like, you worked with hardware or you worked with software?
So initially, mostly programming. Actually, I liked programming a lot initially. I still do, but I don't get much time to do that lately. And then more managerial positions. Part of the time I was working on Java security when I was with Sun Microsystems. And then I was VP R&D for a startup company. And then in 2001, when I turned 40, I said, okay, if I won't do my PhD now, I will probably never do it. So I went to Tel Aviv University. Initially, I approached Professor Yuda Afek, who was my supervisor for my master's, but he was then busy with his own startup. So he said, why won't you work with Nir Shavit, whom I also knew from the period I did my second degree. And I discussed with Nir, and we were both happy to work together on my PhD.
So yeah, to be honest, I thought that you worked with Yehuda because I found this one paper that you did in 95,
My second
1995
degree.
with Yehuda that was published in 2003 after, as far as I remember properly.
Yes, it was published in an Israeli conference and then in the Distributed Computing Journal. And then I took another long break from academy until I returned in 2001.
Okay, so I'm not sure that I understand. So you moved to near Shavit. You decided to work. So was he your supervisor, or was he more a comrade, or like the friend who was guiding you through this PhD
Well,
thing?
he was both my supervisor and still is my friend. I I returned to start my PhD studies, my third degree in 2001. So he was my supervisor during this time.
Sorry for the very strange question, but who is older, you or Nir Shavit?
I would say we are more or less at the same age. Maybe give or take. I prefer that you take give or take 1 or 2 years. We are the same age.
Oh, okay, I see. So, like, wasn't it a little bit strange that you were advised by kind of the person who has
No,
the same age?
no,
No?
not at all. Actually, I thought when I joined the Department of Computer Science in Ben-Gurion University, this was in 2006, so I was 45 years old.
Mhm.
I thought this is probably a record, but then I found out that in another department there was another faculty member who came from the industry and joined faculty even at an older age. So any of you watching us, if you are in your 30s or 40s or even 50s and you want to pursue an academic career, it's not too late.
Yeah, that's really encouraging, to be honest. Yeah. So the question then is: so you seems to be writing on Java, right? Mostly during your high tech industry experience.
No, actually, initially I was programming in a language called PLM, programming language for multiprocessors, which
Hmm.
was used to program those very ancient x86 first processors of this family, and also little assembler for low-level programming. And then later C, little C++, and also Java, but mainly I was working in order to find vulnerabilities in Java security in the not very long duration that I spent in Sun Microsystems.
Can you explain a little bit more what PLM is? Because I never heard about this before this time. So probably you can share. I don't know, Vladimir, have you heard about PLM? I'm pretty sure you are.
No, not really. Well, I do a lot of PL/SQL, but it's I guess it's kind of two-letter similarity only.
So yeah, it would be interesting to learn more about this because it's the part of the history, I guess.
Yes, so actually, before Windows started to dominate the world of personal computing, there was a CPM operating system, control program for multiprocessors, which actually did dominate the the world of personal computing when it was quite small at the second half of the 1970s. And the programming language developed to program this on the CPM platform was the PLM, the programming language for multiprocessors. So that's the language that we used. It was my first workplace after I finished my army service in 1983, and it was used to program on the x86 processor, the 8-bit multi processors that we worked in that project. So it's a relatively simple programming language, not object-oriented even before the object-oriented paradigm started to dominate. I don't have anything very special to say about this programming language.
No, I mean, did it like typically when like back 40 years ago or 50 years ago, nobody really knows how like multiprocessor computers were really to work. So the question is whether it was asynchronous or it was synchronous. Kind of the paradigm of their language.
Okay, no, it was synchronous. I don't recall any intrinsic support in the programming language for concurrency.
It seems that now I understand that you did some multiprocessor things, then you moved to the security, and then you go back when you go. No, sorry.
Yes, I did not work on multiprocessing. I programmed my first years in the industry. As I said, I worked in a medical imaging company and then in other companies. But my focus was not on concurrent computation. It was on algorithms for medical imaging initially, and then for telephony systems, and then Java security. Actually, concurrent computing was never my focus during my high-tech years. So when I did my second degree with Yuda Afek, at around 1990, wow, this is already ancient history, then this was the first time that I started to work on shared memory concurrent computing. No, actually, the work with Yuda was on the message passing model, but I had some conversations with Nir at that time who worked more on shared memory, on the shared memory model. And so I continued to work on this when I started my PhD under Nir's supervision in 2001.
So I have the question then, why, since you were doing more operation, like kind of low-level programming, why you decided to go to concurrency? Why not to like kind of the security that you've been doing or to like operating systems research? Because this seems more relevant to your background.
I like Nir. I mean,
okay.
I chose, or they chose me, both Yuda and Nir, mainly because we had chemistry in terms of interpersonal communication, and the problems they described to me seemed interesting. There seemed to be interesting algorithmic questions and theoretical questions. So I didn't. I could have continued to work on stuff I did in the industry, but eventually I selected according to
your
interpersonal chemistry, let's say.
Okay.
I think both aspects are important when you're considering on what topic to do your research and with whom. It is important that there will be a chemistry with your supervisor. At least you should get along good enough for your work to be productive and for you to feel good. And also, as for the subject matter of your research, it depends on what you want to achieve. If you just want to satisfy your intellectual curiosity, then simply choose according to what seems most interesting to you. If you think to go back to the industry and try to leverage your research, then obviously you should choose a research domain that has some practical applications in the industry. And if you want to pursue an academic career, then also you should take into consideration not only the chemistry that you have with your supervisor, but also it should be a research area that is relatively hot and in focus, and that universities attempt to recruit people who do this type of research for quite a few years. This can be cybersecurity or machine learning or systems. but also other areas, of course.
Okay, how much of your colleagues, like old colleagues, that moved back to the industry? Like kind of not moved back, but moved from the computer science to industry? Because right now, like a lot of people are moving from my perspective, and like how many of yours moved during like last 10 years or so?
Not many. In most cases, if a faculty members would like to pursue a career to work for a few years, either in trying to form and push a startup or to join an established company, then you can take a sabbatical and then a leave of absence. So it's possible for a faculty member to spend a few years in the industry while keeping her position and then coming back. So
Oh, I
most
see.
people will,
So you are
yeah.
kind of safe in the terms of the position.
Up to a point. I mean, if you're absent from the university for too long a duration, then eventually you will face the decision of whether you come back or you give up on your faculty position so that someone else can be recruited.
So most of your works are on data structures. So I kind of envy you, because like it's each year it becomes harder and harder to find an interesting topic on concurrent data structures. Kind of, I don't know why, because a lot of things already have been done. I was wondering why you decided to work on data structures at the beginning, because it was a very huge topic to research then, or because NIR was very interesting on that and you still like continue on that?
Okay, so quite a few of my works are on data structures. I actually looking at this from a broader perspective. I currently conduct research in two areas, in concurrent computing and in cybersecurity. So in cybersecurity, it's not really data structure work. It's more data set oriented work, where you try to identify malicious programs or scripts or computers or email accounts, etc., using techniques such as, of course, machine learning and complex network analysis and other tools. And this is part of my current research. And the other area, which you're familiar more with, is concurrent computing. And some of my works there are on concurrent data structures, but not only on implementing them, but also on the limitations that there are on the complexity or feasibility of implementing them under certain assumptions or certain models. So when I started to work with Neil, then he said, and I think it's a good thing to do when you are supervising a PhD student. He said, okay, while you explore the literature and try to think about a key topic for your PhD research, let me give you a problem to think about that I think is it's feasible to solve it and come up with a solution. So it's always good while you're working at a hard problem to also work concurrently, and to do this concurrently is natural in our research area on other more tractable problems, so that if you get stuck on the harder problem, you still make progress. So this was, I guess, the first more algorithmic data structure kind of work that I did in concurrent computing. It was called still half work queues, a setting in which you have multiple processes, each of them generating work items and consuming them from its own queue. But when your queue gets empty, then you try to steal work from the work queue of another process. And so this was the first work that we did together, and then we did additional work on implementations of stacks and more generally the flat combining technique for synchronization, which is kind of surprising because it says, okay, you work in a concurrent setting, you're implementing a concurrent data structure, but it turns out that it's sometimes more efficient to simply announce the operation that you would like to perform on the shared data structure and then contend on a mutual exclusion lock. And the one who captures the lock then combines the operations of the other threads that are waiting. So it's sequential, but it eliminates many synchronization overhead. So up to a certain level of concurrency, it turns out that it's more efficient than many other implementations. And this was joint work also with the deceased Moran Safrir, who was, by the way, I should mention, a bright student of Nir Shavit, who died at a very young age. So it was really a tragedy. But she contributed actually, I would say she was the key contributor to this paradigm of flat combining. And then additional data structures. But also, as I said, the lower bounds and impossibility results are also a kind of research work that I enjoy doing. And actually, you can't separate the two, because I would say that maybe the moments that are most interesting when you do research is when you're surprised. And for example, when you work on a problem and you're sure that there is an algorithm and you try to devise an algorithm with specific properties, specific complexity, and you try to devise that algorithm and you fail and you try again and you fail again, you hit a wall every time, and then you understand that this wall is unavoidable and that actually such an algorithm is impossible, and you come up with an impossibility result. And the same on the other direction. Your intuition tells you that devising an algorithm with specific properties is impossible. You try to prove it and you fail again and again. And eventually it turns out that the wall that you hit your head against again and again in order to prove the impossibility result is actually a path through which you can devise such. It leads you in the direction via which you can devise such an algorithm. So I think it's hard to separate. If you work on algorithms, then you turn out also, in many cases, working on impossibility results and also vice versa.
I'm not sure why you differentiate concurrent data structures and like lower bounds. I think these are kind of the same thing. Like you kind of talk about concurrent data structures and you talk about lower bounds, but you talk about lower bounds on concurrent data structures, kind of.
No, I meant devising algorithms, devising data structures and algorithms concurrent, but also for sequential data structures. I guess it's the same situation.
Okay, so I want to, when I looked on your works, I was thinking that you started more from the practical things at the beginning, and then you kind of moved more theoretically through years. You kind of then do after the like not primitive, like the standard concurrent data structures, you started from them, then you kind of moved to their STM as everybody moved there, then you kind of moved to their complexity RMR to calculate the complexity of their things. Probably I'm missing some like points where you moved from there, and then you're moving to NVRAM. So did I miss something in between? I'm pretty sure I missed something in between because like from RMR to NVRAM, there are lots of things were done. by you, but like, how did you find each time the new topic, and how, like, because it's not pretty easy to learn new stuff when you should come like to the, like, there is a new topic that evolves, and then you kind of decide, oh, I should move into there. So you kind of read everything what's on this topic and try to push it forward. How did you find, like, because it's pretty hard, so I want to get your advice probably, or your intuition on how to do that, because you seems to be very successful in that.
Thank you. I would say that many times it is the result of simply conversations with colleagues. I mean, back in the day, many years ago, when we had physical conferences and we actually were meeting face to face, then sometimes you would skip a session, don't tell anyone that is less relevant to your research, and sit in the lobby and talk with colleagues, and then you hear about interesting problems, and you think together, and you start to work on a new direction or a new problem. As we know, research is like a Hydra. I mean, you cut one head and you solve one problem, and then this ends up raising a few new problems. So from this sense, you can work in not exactly, but you can work in the same research area for a long time, because there's generally not a problem that there's not a sufficient number of interesting questions to work about. But I do see value on trying to do research that is practical, or can be practical, at least in theory. So, for example, when a new technology such as NVRAM, non-volatile RAM, appears, then and it's quite certain that it will make a significant change in architectures and operating systems, and also on applications and what they can achieve, then I tend to try to do research in such an area. It's not always easy. You need to study, and you need to have maybe colleagues that have started this voyage before you, and you join them. For example, my first work in this direction was with Wojciech Golub. We were together in some event, and then he told me about his work on recoverable mutual exclusion, and more generally, recoverable algorithms are algorithms that in which processes can fail and then recover, unlike the more classical model of shared memory algorithms, in which a process simply fails, stops, or maybe it starts behaving in a Byzantine manner. Here we are talking about a scenario in which you can have a process that fails. Maybe there is a power failure, maybe there is another problem, but then it is resurrected by the system, it starts to execute again, and you would like it to actually find out where it was when the failure occurred, and have it fix the data structure and maybe even complete its previous operation. So this was a feasible and theoretically interesting model for a long time, but the emergence of non-volatile RAM, non-volatile memory, made this model more realistic and increased the motivation to research it, because non-volatile memory can be used as RAM. It is not as fast as DRAM, but the access speeds, difference is not an order of magnitude. It may be a 2 or 3 factor. And so it's a new layer in the memory hierarchy, which is some hybrid between main memory and storage. So if a process fails and then recovers, or even if the whole system fails and then recovers, then the data structure is still there. Unlike conventional systems where if there is a power failure and the processes are resurrected and run again, then all main memory is lost, and you can only try to reconstruct the latest state from storage, which is very slow, and you probably miss a few operations. You can do this much quicker and in a more accurate manner from main memory if the main memory is non-volatile. This is what we have in the new 3D crosspoint technology from Intel, which is already there and also has a significantly larger capacity than DRAM. You have systems with a few teras of NVRAM already, which can be used as main memory either instead of or in addition to DRAM. So inspired by this, Wojciech and his student Ramajau defined a new problem, a new variant of mutual exclusion, which is called recoverable mutual exclusion, which, as we all know, the classical mutual exclusion problem, the algorithm has the structure of either the process is in the remainder section, so it's not really interested in capturing the lock. When it is interested in mutual exclusion, that it performs an entry section, and once it passes it, it's in its critical section, and then in the exit section, the process would like to notify other processes that they can try again to enter to take the lock, and that's the structure. Now, if a process may fail and then recover, then you would like that process to be able to continue from where it was in the mutual exclusion protocol. Specifically, if it was holding the lock, you would like it to be able to re-enter the lock before any other process is able to enter the lock. So Golub and Ramajau defined this new variant of mutual exclusion called recoverable mutual exclusion, RME, and they also presented the first algorithms to implement it. So this is a model in which each process may fail independently, and when a process fails, then it eventually comes up again, and then it has access to the shared variables implementing the lock, because they are in non-volatile memory. But it may have lost, for example, if the process performed a read operation or a swap operation or a fetch and increment operation, it received the value and then it crashed, then this value is lost. So the challenge is how to extend existing mutual exclusion algorithms or devise new ones that solve this RME, this recoverable mutual exclusion problem. So in their work, they implemented a recoverable mutual exclusion algorithm, an RME algorithm, using reads and writes only with a log of n remote memory references complexity. So I should mention that the metric used to quantify the complexity of mutual exclusion algorithms is for 25 years or so is to count the number of remote memory references. Put simply, these are the references that cannot be serviced from the cache, but you need to traverse the system interconnect in order to read the variable or to write to it from the main memory or from another cache. This is simplified, but you don't count all the memory accesses, only those that are remote. So their algorithm, as I mentioned, used only reads and writes and achieve a logarithmic log n remote memory references, where n is the number of processes that use the lock, that share the implementation. And this is actually tight because there's a previous lower bound by Atiyah et al. That shows that you cannot do better if you only use reads and writes. But as many of us know, there are algorithms that use other operations on shared variables, not reads and writes, but for example, swap and compare and swap, that achieve better complexity. For example, the MCS algorithm, the Mellor-Cramian-Scott mutual exclusion algorithm, achieves a constant number of remote memory references per what we call a passage, that is an entry and then an exit of the critical section. So when you consider, let's call it conventional mutual exclusion algorithms, that is not non-recoverable mutual exclusion algorithms, then there is a separation between reads and writes, in which the algorithm must incur a logarithmic time complexity. Actually, it's not only reads and writes, it also compare and swap and test and set. And between algorithms that can use other well-known operations such as fetch and add and swap, where you can do it in constant time. But Wojciech and his student tried to devise a recoverable mutual exclusion algorithm that has sub-logarithmic complexity, and it turned out that it was not trivial to do so. So this is the result. Back to your original question of how do you get to work on a subject that you didn't work about before. So here, for me, the migration was natural because I worked on mutual exclusion algorithms and impossibility results before. And here there was another problem in this domain, motivated by the emergence of this new technology of non-volatile RAM, which Wojciech and Ramaraju formally defined as the recoverable mutual exclusion problem. So it was a natural question for me to think about, so which eventually you can get to think about other problems in this new model where processes may fail and then recover again and again.
Yeah, can you please clarify what happens if the process doesn't really recover? So if it fails, I mean, if it takes the lock, dies, and then never recovers, is it in the model or it is not considered to be in the scope of the algorithm?
Okay, so actually it is in the model. There is not, to be precise, there's not one model, but there are actually many models, both of the crash recovery, how crashes and recoveries occur, and what properties you need to have in order to call your algorithm recoverable. The key distinction is between system-wide failures and individual failures. So in the system-wide failures, you assume that the whole system fails, and then eventually the system comes up again, and then each process may eventually recover and try to continue maybe from the point where it failed, but you don't necessarily have to rely on it, and this depends on the progress properties that you require from your algorithm. So, for example, you may require from your algorithm a strong property called wait freedom, which means that any operation that a process performs, and this operation is actually executed or implemented as a sequence of steps, let's call them such as read or write or test and set, then after a sufficient number of such steps, this process will complete its operation regardless of what happens with other threads or other processes. So even if other processes are very slow, even if they fail and recover, or even if they fail and don't recover, then your operation, that process's operation, will eventually complete, only depending on the scheduler giving it enough opportunities to perform more steps. But there may be algorithms in which, for example, upon recovery, you do rely on that every process that failed will eventually recover, will perform the recovery code, and only then can you ensure that the system as a whole can proceed after the fail. So there is the system-wide failures model, and there's also the individual failures model, which was actually considered by Wojciech and Ramarajo in their formulation of the RME problem, where each process may fail and recover independently, while other processes may proceed normally without failing. I hope this answers your question.
Thank you very much, Danny. It seems since you're too talkative in the sense of NVRAM, yeah. So this means that are you more satisfied with NVRAM than other topics that you have done, or like why so like you're so encouraged to do that?
Okay, first of all, let's get back to the point that you mentioned before, that I don't have much time to do research over the last year or so. So I'm talking about the last research works that I did, and contemporary ongoing work that I do with students in this period in the realm of concurrent computing.
Mm-hmm.
I find it useful since, in any case, I split my research time between cybersecurity and concurrent computing, at least in concurrent computing, to try to be more focused on this area. So this is why I'm talking about this more than I do about other areas of research that I'm still interested in, because these are my latest. This is my latest work and contemporary work.
Yeah, I mean, you really enjoy it. So like, as you told everything, you really enjoyed it, and like I like how you solve these problems. Like about NVRAM, I have the question though. So there are several points in the world who are working on NVRAM right now. What do you think? Who is their closest one in the sense of their theory side, closest to the edge, and who are more closest to the practical side? Like I know that I'm pretty sure that theory is already going much more forward than practical, but what do you think about their state of the art right now?
Well, I would say, well, I don't have as much time as I would like to follow up on very recent development, but I think that both theory and practice are making progress on this topic, and we're also involved on a project that deals with more practical aspects. So, for example, of how can you leverage this new type of memory for supercomputing or for HPC applications and architectures. And I know that in our community, when I say our community, I mean the concurrent computing, the PODC, disk, SPA, PPOP, etc. There are quite a few people who work on both the theoretical and more practical aspects, but I'm sure also in other communities that I'm less familiar with, such as the systems and architectures, and of course HPC. because this is a significant technological change that can have implications in many areas of both research and practice. So I can I don't know, mention specific names, but I don't think it would be very useful to do so. Everyone who would look at the papers showing up in POTSI, in DISC, in SPA, in PPOP, etc., then there is quite a few on these areas. So, but there are also many other interesting questions in concurrent computing, and not all of them are practical. For example, there is a very interesting problem defined by Yuda Afek more than 20 years ago of whether the Q object is a member of the common 2 class. These are the objects that can be implemented by any consensus 2 object. So this is a purely theoretical question, and there are some problems that are theoretical, but you can give them a practical motivation. So this is a theoretical question that I cannot think of any practical motivation, and still it would be very interesting to solve. So as you do your research along the years, then there are some problems that you are not able to solve, and that you go back to once in a while, if and when you have the time to see whether you have a new angle to do something with them, or maybe one of your students will have a new angle to tackle them.
Like I wanted to really ask the question whether, because there are lots of theoretical work which are kind of probably even not connected of them, and there is a lot of different models that are come up. When do you think we can end this finally in the NVRAM topic? Like when everything will be under one whole model or something like that?
I'm not sure this will ever happen, because, for example, if you think about what model of failures and recovery is more natural, then some people claim that the model of individual failures is not realistic, because you have a server with this, I don't know, let's say 64 cores, and the realistic scenario is that there is a power failure, and so there is a system-wide crash, and you need to recover from it. So it was claimed that the individual failures is not realistic. But when you look at the setting of supercomputing and HPC computing, where you have many strong servers communicating together in order to perform some very large scientific computation, then you see that individual failures are really not a theoretical question anymore. It's reality. You have many different devices, different servers working together, and once in a while one of them has some problem, maybe a hardware problem, and then you need to recover from this. So I don't think we will get to a situation in which there is just a single interesting model for this let's say, for this type of problems that are motivated by non-volatile environment. Also, recoverable algorithms are just one aspect of new work that has to be done because of this new technology. And operating systems have to be maybe redesigned or extended, and new file systems are being developed that can leverage, for example, the fact that you can now access non-volatile memory not in block granularity, but rather in byte level granularity, or actually cache line granularity. Also security implications. I mean, when you have a conventional system and there is, let's say that you would like to, you have physical access to the computer and you want to take out the memory and immediately analyze it to try to extract cryptographic keys. So it's more difficult to do this when this information, this private information, is in DRAM, because rather quickly the information in the DRAM is lost. By the way, not immediately, and there are quite a few works on how you can reconstruct it within some window of time. But when this is NVRAM, then it's much simpler. So you need to rethink how you partition the information that your application needs and the data structure it uses between DRAM and NVRAM. So recoverable algorithms are just one class of problems, or one sub-area of research that I would say is motivated by this new type of technology.
So do you work on NVRAM in your security works?
So far, I did not get to do this. Maybe in the future, I will.
Okay,
but not yet.
Okay, great. I have an interesting question which you partly answered because you already thought about this topic, about the very old questions that are kind of stuck, being unsolved. Can you tell me, probably you have a question, like, is this you the question about Common 2, or there is another question that bothers your mind for a very long time?
There were a few questions that were solved over the years. Of those who were not, this is certainly one of the most challenging because it's elusive. I mean, it's not even. I don't have a clear intuition whether there is an algorithm there or any possibility result.
So you haven't found your wall yet, where you describe that kind of when you do research, you're stuck with the wall.
Oh, there is a wall, but I'm not yet sure. I don't know whether this wall is indeed a wall and there's no algorithm, or whether if I will bump my head strong enough against the wall, then something will crack or will give me an indication that I can circumvent the wall in a certain manner and get an algorithm. No idea.
When you say partial failures or individual failures, do you consider thread failures as well?
Yes, actually, I mean thread failures. Yes.
Okay. In Java, we have quite a common case for stack overflow error, which is when the process grows up the stack, it fills it completely and it fails. And it happens so that it just keeps the variables in unrecoverable state. So basically keep all the logs locked. Do you think NVRAM could automatically fill this? Or is it like impossible?
So if in this scenario that you describe, if these variables would have been stored in the address space of NVRAM, then the system could try to resurrect this process, and then it would have some work to do in order to know exactly where it failed, because the model I described before when I talked about the recoverable mutual exclusion is more abstract than reality, as is always the case, because in reality, for example, caches are volatile. So it might be that you work with non-volatile variables that are in NVRAM, but the latest values that you have written are still in the cache. And so you need to, when you recover, you need to account for this. And there's another problem that when you do several writes in program order, they will not necessarily be persisted in the NVRAM in the order that you made them. So there are hardware instructions in order to overcome this, but you need to take this as well. But it is possible in the scenario that you've mentioned to enable such a process to recover based on the state of the data structure that was there when it failed. Yes, certainly. Maybe it's an interesting direction, needs to be looked into.
Yeah, and one more question regarding security. And I wonder if you are familiar with the security manager in Java. That is, the approach Java tend to use to make secure by default, configuring the set of allow or forbidden methods to be executed by code here and there. And now they deprecate it for removal. So they mean the security manager is gone. So there is no one in core Java. What do you think about it? Was it feasible approach, or is it something that should...
Okay, I'm actually not familiar with this change in the Java security approach, but now that you mention it, I'll try to catch up on this. But unfortunately, I'm not familiar with the topic, so I can't say much about that.
Yeah, thank you. Thank you. That was great history. I mean, that was nice story, and thank you for all of that.
Yeah, I mean, it's pretty amazing when you have an NVRAM expert here. Kind of not of the hardware, I think, but in theoretical sense, you're an expert anyway.
Well, you know, the classical definition of an expert, it's someone who knows more and more about less and less until eventually he or she knows everything about nothing. So,
will it get to eventual consistency, or with all other experts?
It's convergence in the strong sense, but
convergence in the strong sense.
Well,
that's good.
You need to try to balance between exploration and exploitation. I mean, on the one hand, in order to do significant research, you need to know much about relatively narrow research areas. On the other hand, if you are not sufficiently knowledgeable in other areas, then you may miss techniques that may help you do better work in what you research. So I would say that I'm knowledgeable in certain aspects of recoverable algorithms for NVRAM, but it's a very broad area. And yeah, so I'm sure there are many researchers who are more expert than me on many aspects of NVRAM.
So I think we're almost done, in the sense we're already kind of running out of time. So thank you very much, Danny. Thank you very much for coming. That was really interesting talk. Like you probably someone will see our discussion. They will understand that they want to work on the NVRAM right now. So I hope that you kind of encourage somebody to do that, and probably you will find new collaborators after that.
Thank you. It was fun also for me.
So I hope you very best, and hope you very good results in NVRAM and etc. And wish you health, very good health in this COVID times. Thank you very much.
Thank you. Same to you. It was a pleasure.